In our previous lesson, we were talking about the Pythagorean theorem. Well, we have a twist on that today because now we're talking about the converse of that theorem. So right up here at the top above that box, this is the Pythagorean theorem. Notice it's more than just the formula. It is represented as a conditional statement. We call that an if-then statement. So if a triangle is a right triangle, then the formula works. C squared equals A squared plus B squared. And today we'll talk about why we have the C squared on the left-hand side instead of the right-hand side, but you could write it the other way around here. Now, what this is saying is that if the triangle is not a right triangle, then the formula will not work. As long as it's a right triangle, you can proceed with the equation. Now, the theorem exchanges the hypothesis with the conclusion of that if-then statement. And you're going to see that summarized right down here at the bottom of that box. If this equation is true, if C squared equals A squared plus B squared, then that means the triangle you are working with really is a right triangle after all. And so we can now use this to test our triangles to see if they are right triangles or not. In this diagram here, we're representing the concept of we don't know if that's a right triangle or not, but we can check it with that formula. So let's get started with example 1. We have 2 illustrations here. Let's tell whether the given triangle is a right triangle or not. Notice there is no right angle, okay? But if there is one, it would belong here. These sides look to be parallel, we just don't know if they are. Same with part B. We don't know if this is the right angle or not, but it looks to be parallel. That's where the right angle would belong if there is one. So we're kind of assuming, first of all, where the right angle would be found, so that opposite that right angle, we would get to our hypotenuse. So this gets that letter C, right? And then again, it doesn't matter which is the A and which is the B, but we do have to make sure that the hypotenuse that we're thinking of would be positioned across from where the right angle is. Now, another way to check on that is the hypotenuse is always the longest side of the triangle. Here we have a 6, here we have a 9. How would we know if this is a longer side? Well, we can check real quick just by verifying its decimal value is in fact bigger than 6 and 9. I should say it's bigger than 9. So if we take 3 square roots of 13, we can do an approximation, and there it is at 10.8. So yeah, it is the longest side. That means it is the hypotenuse. But when we do our calculations with the formula, don't use the decimals. It could be ever so slightly off. We're going to use the given values in this case. Now for this work that we're doing, we definitely want to make sure that the C squared is on the left-hand side. We'll get to why that is in the next section, but it will help that transition a little easier. So here's our hypotenuse. We have the 3 root 13. We have to square that whole value, and that equals the 6 squared plus 9 squared. So we've seen this from time to time. Remember, this means you have 2 identical copies of this that's being multiplied to itself. So you have a 3 root 13 times another 3 root 13. So what that means is you have a 3 times 3, which will give you a 9, and you have a root 13 times another root 13, which turns out to be exactly 13. And we still have to multiply those together just like these were multiplied together. 6 squared is 36, 9 squared is 81, and so I'm multiplying 9 times 13, and my calculator gives me 117. We're going to add up the 36 plus 81, and look at that, it gives us 117. That is a true statement. If you have a true statement, that means it satisfies, these values satisfy the equation, which means that our triangle really is a right triangle after all. So we will say, yes, this triangle is a right triangle. Here in part B, we have a side of 16, 24, and 29. Obviously, the 29 is the biggest of them all. That one will get the letter C. That's the potential hypotenuse. Again, it doesn't matter which is the A or the B, but I'll go ahead and label them on here. Here's our setup. So we have 29 squared equals 24 squared plus 16 squared. And my calculator tells me 29 squared is 841. And my calculator tells me, I'm just typing this in all at the same time. 24 squared plus 16 squared, my calculator gives me 832. Now, these are clearly not equal. So update your symbol. We assumed they were equal for the purposes of starting with the equation. But now that we know they're not, change that to a not equal sign. These values did not satisfy the equation, which means this triangle is not a right triangle. Now, if it's not a right triangle, that means there's only two other options. It's either an acute angle, so it's an acute triangle, or maybe that's an obtuse angle, so this would be an obtuse triangle. And we can actually figure that out. And that's where we're headed next. And this is why we were putting the c squared in front, as a way to help us with this little memory trick to help us figure out what we have in each of these three cases. So far, we have been looking at just this first case that you see here on the left-hand side. If c squared equals, there's your equal sign, the a squared plus b squared, then that means you really do have a right triangle. That angle C will be a right angle. So it has to be 90 degrees, and therefore we have a right triangle. However, in the second case, if your value of c squared is less than the numbers you get with the a squared plus b squared, then that means your angle C is less than 90 degrees. So if the angle is less than 90, it's an acute angle, and that means we have an acute triangle. And then in the third case, if your value of c squared is in fact bigger than, greater than the number you get with the a squared plus b squared, then that means your angle is bigger than a 90 degree angle, which means you have an obtuse angle, which means you have an obtuse triangle. So let's take that concept back up to this example we saw earlier. This was our c squared, and we said that c squared value got us 841. So we want to know, is that smaller than 832 or is it bigger than 832? So we can say 841 is in fact greater than 832. What we're representing here is the case of our c squared value is greater than the a squared plus b squared value. So you can see right here, if the c squared is bigger than the a squared plus b squared, that means our angle is in fact bigger than a right angle. We actually have an obtuse triangle in that above example. So that's what we're going to be doing. And it's for this reason that we put the c squared on the left-hand side. If you switch the equation around so that c squared is on the right-hand side, then you also switch the direction of the inequality, and then you don't have this nice pattern to help you memorize whether it's bigger or smaller than 90 degrees. So that's why I recommend you keep the c squared on the left-hand side, and I will do the same for these next couple of examples. If your c squared is smaller than the a squared plus b squared, then that means your angle is smaller than a right angle. If it's greater than the a squared plus b squared, then that means your angle is greater than a right angle. So here are a couple more examples just to finish it off. Let's classify the triangle as acute, right, or obtuse. Here we have lengths of 2.8, 3.2, and 4.2. That's obviously the biggest side. That gets the letter C, because that has the potential to be a hypotenuse. So we're going to set this up using c squared on the left equals a squared plus b squared. Now again, we don't really know if it's equal or not, but we're starting off with the equation, and then we'll test the results afterwards. Our value of c is the 4.2, so 4.2 squared equals 2.8 squared plus 3.2 squared. Again, we'll take that to our calculator, and that gives me 17.64. I can type all of this in my calculator at the same time, and that will give me 18.08. All right, so I left that sign blank in the middle so that I could compare the results. The 17.64 is smaller than 18.08, so that's the less than sign. That means our c squared is smaller than the a squared plus b squared. That means our angle is smaller than a right angle. That means it's an acute angle. Therefore, we have an acute triangle. And that is representing that middle case right there. Here's another one with decimal values, 6.1, 9.4, 11.3. Again, 11.3 is the largest. That is your potential hypotenuse. Setting up our formula again, we have 11.3 squared equals 6.1 squared plus 9.4 squared. And again, just taking that to our calculator, we get 127.69. And then on the right-hand side, all of that becomes 125.57. So the 127 is greater than the 125, so that's the greater than symbol. That means our c squared is greater than our a squared plus b squared, and therefore my angle on the triangle is bigger than a right angle. So we have an obtuse angle. Therefore, we have an obtuse triangle. And finally, here in this last example, it says, could you use triangles with side lengths of 50, 120, and 130 inches to verify that you have perpendicular lines? Okay, so think about this. We know perpendicular lines form right angles. So it's saying, do you really just have a right triangle in this case? We're still using the same process. The largest side gets the potential hypotenuse. We're testing the formula. 130 squared equals 50 squared plus 120 squared. And so, again, we're going to take a look at what we have here, and our calculator with these very big values gives us results of 16,900 on both sides. So that is a true statement. It's neither less than nor greater than. That means c squared really does equal a squared plus b squared. That means our angle equals a right angle, and we have a right triangle. So now that we know that we have a right triangle, we understand that a right angle exists, and if you have a right angle, that's formed with the perpendicular lines. So we have the right triangle. So there is a right angle. So the triangle has perpendicular sides.